All right, so we're in section 12.2, part 2. So we're going to integrate vector value functions today. So what we're going to do with integration, it really just follows on from how we find differentiation of vector value functions. So if we have our vector value function r of t is f of t I plus g of tj plus h of tk, our generic vector value function, and we want f, g, and h are continuous on some interval, so where we have nicely behaved functions, that the integral of r of t, r not d, getting ahead of myself, r of t dt, we just integrate component by component. So this is going to be the integral of f of t dt I hat plus the integral of g of t dt j hat and then we do the integral of h of t dt k hat. And if we want a definite integral on some interval a to b, we just do the definite integral of each piece. So same thing, we're just adding our limits of integration on here. So nothing more complicated. We just end up doing everything with a vector value function if we're in 3 dimensions, doing everything 3 times. Now, one thing we have to be careful with vector value functions is when we perform an indefinite integral, what do we always get when we perform an indefinite integral?
Plus c.
Plus c. But here, because we're dealing with a vector value function, our constant of integration is a vector. Doesn't make it particularly difficult. We just need to know some initial conditions to find our vector constant, and the initial conditions will also be a vector. So we have our constant basically for each term, each piece, each component. So we just have to be careful and remember, because we're dealing with vector value functions, that are constants of vector. So we could write the integral of r of t dt equals capital R, whatever our antiderivative is, r of t plus c, where the derivative of r equals r. So capital R is our antiderivative. So that's really the only different thing that we have to be aware of is that our constant of integration is a vector, and we integrate component by component. Nothing different, nothing new, nothing unusual. We just have to remember this piece. Any questions there? Okay. So I have some more true or false questions. I love these true or false questions. So we're thinking about vector valued functions here. So our first true or false. We have a particle moving on a sphere. So true or false, we want to know the derivative of the position vector is tangent to the sphere. So we want to know true or false on that. So we have this particle moving around on the surface of this sphere. Is the derivative of the position vector tangent to the sphere? We want to know true or false. Got a couple tentative truths there. So think about it for a minute. So if let's just simplify it just a little bit and take a cross section and say for the moment, so this is a cross section of the sphere, that our particle is moving around on that circle. So is the derivative of the position vector going to be tangent to that circle? Yeah, you kind of think so. So if we extend that to the sphere, we would say this is true. What would happen if the derivative of the position vector was not tangent to the sphere? What would that tell us about the motion of the particle? So if we were saying that we have this particle and as it moves, the derivative is tangent to the sphere, so something like that. So what if it wasn't tangent?
Probably not moving.
Well, would it have a... So here, at this point, because it's tangent, are there any components of this vector taking us anywhere but on the circle? So think about a particle on the sphere. If its derivative vector is not tangent to the sphere, it's going to have a component either towards the sphere or away from the sphere, if it's not tangent, right? And if the derivative has a component towards the sphere or away from the sphere, what's that going to do to the particle? It's going to take it either towards the sphere or away from the sphere, and then it wouldn't be moving on the surface of that sphere. So if it's moving on the surface of a sphere, the derivative of the position vector has to be tangent. Otherwise, we would have some component of the derivative towards the sphere or away from the sphere, and our motion would be towards the sphere, away from the sphere, and take us off the surface. So this is true. This one should be easy. The definite integral of a vector valued function, so we're putting some limits of integration there. The definite integral of a vector valued function is a real number. So we're putting in numbers and we're calculating. So we want to know true or false there. What is it? It's a vector. The definite integral of a vector valued function is a vector. So when we take our definite integral, we have an I component, a j component, and a k component. So the derivative, or the integral, the definite integral is a vector. This one takes a little more thought. So the derivative of the magnitude of the position is equal to the magnitude of the derivative of the position vector. So the rate of change of the magnitude of the position vector, the magnitude of the position vector, is that always equal to the magnitude of the rate of change of the position vector? We have some falses. So what would be an example? What would be an example of where this would be false? Those of you that said false, can you come up with a counter example to this problem? So what is the rate of change of the magnitude of the position vector? How could we describe that in kind of everyday language? We're thinking the rate of change of the magnitude of the position vector. So the position vector is just basically the magnitude of the position vector. We could think of that as how far away we are from the origin. So this is the rate of change. We could think of this as the rate of change of the distance from the origin. And the magnitude of the derivative of the position vector would be, what would that be, Josh? I think that's what you're thinking of before. That would be since we're taking the magnitude, that would be the speed. What was it? If you're moving?
I mean, if you're moving on a sphere, then the distance from the center stays.
Right. So there's our counterexample. If we're on the surface of a sphere or on the plane, uniform circular motion, the rate of change of the position of the magnitude of the position is the radius. Uniform circular motion, the radius is constant. But is the speed constant?
I mean, not necessarily.
Not necessarily. Well, so the rate of change of the radius is what in uniform circular motion? 0. We have the same radius. The speed in uniform circular motion is not zero. It's a constant in uniform circular motion. So in uniform circular motion, we have the same distance from the origin. So the radius is not changing. We could think of this as the radius. This is the speed. The speed is constant. So this would be 0 in uniform circular motion. This would be a constant. So that would be our counterexample in uniform circular motion. Uniform circular motion, change in our magnitude of our position vector is just the radius of motion. So that's going to be 0. And the magnitude of the rate of change of the radius, the speed, equals a constant, which is not necessarily 0. So those two would not be equal. So this is false. That one took a little more thought. All right, last one. The derivative of R of t dot u of t equals r prime of t dot u prime of t. True or false on that? Got some falses pretty quickly then. Several falses. What do we have to use here when we take the derivative of the dot product? We have to use a product rule. So this is false. We need a product rule. Or we could take the dot product first and then take the derivative. But we can't just take the derivatives. We can't just take the dot product of the derivatives. So this would be false. We need to use a product rule. Questions? All right, that's all I wanted to say today. The homework, just practicing doing integrals with vector value functions. Nothing complicated, no new concepts, just integrating. Remember that your constant of integration is a vector.
I